Okay, so we have various types of beams and loading and support. Okay, so what is a beam? A beam is a structural member designed to support loads applied at various points along its length, right? So we talked about that already. So let's talk about the loads for a second. Beams can be subject to concentrated loads or distributed loads. So here's concentrated load. So what does that mean? So this beam is sitting across this, say, span, and you have a point here and a point here with loads on it. Versus a distributed load, this is stuff we did in chapter 5, right? So W is in some force over distance, and this is the area of that distributed load. So beam design, when you're designing a beam, it's really a two-step process. Okay, you want to determine the shearing force and bending moments produced by the applied loads, and you want to select the cross-section best suited to resist the shearing forces and bending moments. So what does that mean? So you're designing a bridge, right? You're a civil engineer, you're a structural engineer, you're designing a bridge, and say it's a bridge for a train. So hey, when the train is fully loaded, it's coming over here, it's going to be really heavy, and so it's going to produce a pretty significant amount of shearing forces and bending moments. So you're going to go through and you're going to try to map or try to determine what are the shearing forces by this train driving across the bridge, or what are what are the bending moments of this created by this train driving across the bridge? And then you can go and you're going to select a product, a material to build the bridge out of that's best suited to resist the shearing forces and bending moments. So, does this need to be built out of 2x4s and cost like next to nothing, or do you need to build this out of super hardened steel, I-beams that are 10 feet high? I don't know. The point is that's what beam design is, and so that's what we're doing in this chapter. Is we're learning how to determine the shearing forces and the bending moments, so that you could then make those decisions to pick the right thing to build stuff with. Okay. So there's various types of beam loading and support. So these are statically determinate. We did this, I think, in chapter 3 or 4, right? So here we have 1, 2, 3 unknowns, right? Here you have X and a Y, and this one you just have a Y. So it's a simply supported beam. So nice and three unknowns, we can do that. Here we have overhanging beam, right? You have a X and a Y here, and in this case you only have a Y. So still 3 unknowns. Here a cantilever beam. So again, here you have X, Y, and a moment, but still just 3 unknowns. So in 2 dimensions we can solve all these. We're good to go. So those are beams that are classified according to which they're supported. So the reactions of beams are determinate if they involve only 3 unknowns. So all these are statically determinate. In other words, you can solve for the unknowns. Otherwise, they're statically indeterminate. So, this one, you have 1, 2, 3, 4 unknowns. So no matter how much we try, no matter how hard we try, we have in 2 dimensions, we have 3 equations, right? Some of the forces in X, some of the forces in Y, and some of the moments are equal to 0. You just get 3 unknowns. You cannot solve for more. Here you have 1, 2, 3, 4. Here you have 1, 2, 3, 4, 5, 6. Okay, does that mean you can't physically build something like this? Of course it doesn't mean you can't build something like this. Anyone can see that you could just do this anytime. Here, you could put 15 different supports under here, and you can obviously do these things. For this class, what we're going to be dealing with is we're going to be dealing with statically determinate beams and loading on statically determinate beams so that we can figure out these unknowns. So why does that matter? Well, for this reason right here. When we're determining the bending moment and the shear in a beam, okay, what we're going to do, so we have a beam and it's subject to some forces. And this is an example, so we have some concentrated forces and we have some distributed forces, okay? The first thing we need to do is determine the reactions at the supports, and that's why we have to be dealing with statically determinate beams. So we're going to replace these supports with the forces, the reactions at those supports. You notice this one could technically have an X direction force, but we don't have any X direction because all the forces are vertical. So there you go. So the X is 0, but then you have RA and RB. Okay, and we're going to treat this whole thing as a free body. And then what we're going to do is we're going to go through it and cut it at various places. Okay, so we're going to cut this beam. So here we're going to arbitrarily, this C right here, we're going to just arbitrarily cut it right here. So let's look at just this part right here. Well, we know RA because we looked at the whole thing, right? We know P1 because it's given. We know the load, 1. Now there's also a shear and a bending moment to stay in equilibrium. I mean, how do you know that? Well, quite frankly, because when you do the math, all of these forces end up being equal to these 2 forces combined, right? All the ups equals the downs. And this force, it's extremely unlikely that at this point it's going to be equal to that. And so what ends up happening is this shear force is compensating for the difference, right? Because again, everything needs to be in equilibrium. This part is in equilibrium. Now, I mean, obviously, if you cut it and you just left it there, it wouldn't stay in equilibrium, right? But if you were to somehow look at the forces inside, it's going to be in equilibrium. So we're going to cut this at some arbitrary point, and we're going to determine the shear force that would be required to keep this section in equilibrium. Or, you'll notice this V and V prime. You can look at this shear force that would be required to keep this section. It's going to be the same thing. And then the moment to keep this section in equilibrium, and the moment to keep this section, I guess really, or the moment. So you can solve for V and M, or you can solve for V prime and M prime, kind of whichever one's easier, right? You pick the one that you want. There is a correct sign, a correct sense for these. These are the standard sign conventions. A moment that makes it kind of smile is what I call it. When it makes it bend so it curves up, those are considered a positive moment on either end. So this is a little bit confusing to me. So if you cut it, the positive sign on the left-hand side of the cut, the shear force going up is going to be positive, and the shear force going down. This is true, the negative version of that, but just to me, although it's true, I'd say it just kind of confuses the issue a little bit. So let's focus in on this, right? So by definition, the sense for internal forces, the smiley face is a positive moment, and a shear force on the left side is up is positive, or on the right side down is positive. So those are the definitions. They're obviously arbitrary, right? You can have anything, but those are the definitions that we're going to use for shear forces and bending moments. Okay, so we're going to make a bending moment, a shear force and a bending moment diagram so we can kind of visually see what's happening here. Okay, so variations of shear and bending moment along a beam can be plotted, right? Because you can picture this. So right off the bat, there's going to be P over 2 on both sides. And so if you're right here really close, you're going to have different moments and different shears. Okay, so here we go. We're going to determine the reactions at the supports, just like we talked about. We're going to cut the beam at various places. And then we're going to consider either this side or this side. I'm arbitrarily going to pick this side, right? So let's look here. So what is V going to be? Well, since there's only one force going up, it has to be that same equal force going down. So the V going down, which is positive, we decided on the right side of the cut, a downward shear force is positive. It's going to be P over 2. And then moment. Well, the moment's going to change, right? So if I cut it really close, that X is really small, then say I take the moments about point A, the moment is going to be V times X, and I have to undo that if you'll have to compensate for that. So as X is small, it's going to be really small, and as X gets large, the moment is going to become large. And you can go through and you take it at various points. So we're going to take it here, 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 right, at different points along the line, and you can keep on solving for that. If we look on this side, this is just the same equation, but going from the right side instead of the left side. So for a beam subject to concentrated loads, shear is constant between the points, and moment varies linearly. So again, does that make sense? Right here, if I cut it here, there's still only one force on this side, and it's P over 2, so that force down has got to be P over 2. Right up until just before this point, right? There's still only one force, so the shear all along here has to be P over 2. And then you get on this side, and then if I cut it, I can either look to this and say, well, clearly it has to go down. Remember, now we're on the left side, so that's a negative. Or you can keep on looking. I'm inclined to keep on looking at the same side. So let's look right here, right? You have a force here. I have P over 2 and P. So in total, there's still P going down. So now I have to put P over 2 going up, which is the negative shear force, which is right here. So you see that the shear is constant. Constant between concentrated loads. So it stays P over 2 until that load then swaps down here to P over 2, and then it goes back to 0. And then the moment, again, the further you get away from that point, when this V is super, super small, if it's right next to that point, the moment's almost 0, right? So if it's right on that point, the lever arm is 0. So there you go, you have 0 moment arm. And as you get further away from this distance gets bigger and bigger and bigger, and that moment gets larger until you have a peak right here, right, where that force is applied. And then you start going the other direction, right, because the shear is in the other direction. So Let's do a little more fleshed out example of this. We'll do example 7.2 from the book.